Hi, in this tutorial we're looking at examples of probability and using the normal curve in Excel. So down here you can see we've got an example of a discrete probability problem using the addition rule, discrete using the multiplication rule, discrete contingency table problem, and then we move on to continuous probability looking at the uniform distribution, the exponential distribution, and finally the normal distribution. And we include the z-distribution here for reference. So let's start at the beginning here. So the problem for the discrete addition rule says the following students are enrolled in a course in sociology. They're listed along with their year in school and major. What is the probability of selecting at random from this class a sophomore? So here's our table, right? So we have our students 1 through 10. There's their class levels and there's their major, whether or not they're a sociology major. So the first question is just asking about sophomores. So what proportion of the students are sophomores, right? So there's our probability. So we're just simply I created a separate frequency table down here that collapses this information. So we have freshmen as sociology majors, yes or no. Sophomore as sociology major, yes, no. Junior, senior, and from that you can see that what we're doing when we're looking at probability of drawing a sophomore is we're adding the probabilities of the yes and no. So we're ignoring the majors, so we're just adding those together. So it's 0.4 plus 0.1. The second one is a student majoring in sociology. So that's going to be adding together everybody who said yes to that item, right? So when we look at this probability, we're just adding up the yes probabilities, right? So 0.1, 0.4, 0.1, and 0.1 gives us 0.6. That's a 0 down there. Okay, I had to double check that. It didn't look right. And then it says a freshman or a sophomore. So for that one, this is the addition rule. When you see or, we use addition, right? So we're combining freshman and sophomore as the target. So the probability of getting a freshman combines the yes and no for freshman, and for sophomore combines the yes and no. So we're just adding up all of those values. And then not a freshman, that's the Q value, right? So if we know what freshman is, right, we're just adding those up, 0.1 plus 0.1. But since we're looking at the Q value, it's 1 minus 0.1 plus 0.1, or 1 minus 0.2, just give us everything but those values. Or we can just add up, as we've done here, all of the probabilities that don't include the freshman. And that's how we work with the addition rule. The next sheet here uses the multiplication rule. So it says, suppose that 2% of convicted felons are in fact innocent. Hey, if a person is convicted of a felony, what is the probability that they're guilty? So if it's a 2% chance they're innocent, then we're looking at the Q value. They're not innocent as guilt, right? So that's probability of guilt is going to be 0.98, right? So, but what if we look at two people convicted of felonies? So here they both have to be guilty. We're going to use the multiplication rule. So we're going to start with one person, multiply it again by 0.98. So two people, 0.98 probability is 0.98 times 0.98. That gives us 0.96. And then we continue that way when we add our third person and our fourth person. And you can see what's going on here. As we add people, the probability that all of them are guilty declines, right? At some point, you can imagine when you get to a larger number, this is going to start getting closer and closer to a coin toss, right? 50-50. So if you have 100, and you could calculate this by just extending this table, you could find, a relatively low percent that they're all guilty. It's kind of an interesting statistical probability phenomenon. So let's look at a contingency table. So here uh, we have a table of musicians, the way that they learned their craft, how they learned to play music, and we have gender. So really the goal of this table is to see if there's a gender difference in the method of learning music. So we have 72 females and 58 males of private instruction. There were 22 females and 15 males. And then we have studied in school and self-taught. So it's asking us, what is the probability of being a musician and a female? So that's just all females, right? So that's 72 out of all the musicians, 72 out of 130. So there's our formula for that, F5 out of F7. And that's about, it's 0.55 or 55%. So most musicians are female in this particular sample. Then it says probability of musician is a male and had private instruction. So now we're limiting male private instruction. Okay, so we're looking at that E6 cell. And then we're dividing that by the total of all the musicians. So it's just 15 over 130. So only 11%, 11.5% of musicians are males with private instruction. And then this OR thing, right? Remember how we do that? So the musician is female or self-taught. So we have female, so it's 72 out of 130, plus being self-taught, which is 12 out of 130, but then we have to separate out the females who are self-taught because they're being double counted. So you see in the formula here, we're subtracting C5 over F7. Okay. So we have females over the total, we have self-taught over the total, females self-taught over the total, and then we're subtracting out 12 from the overall calculation to give us 0.7. So this gets a little more complex as we start changing the parameters of our probability. Let's move on to continuous probability. This one uses a uniform distribution. So it says a fireworks show is designed so that the time between fireworks is between 1 and 5 seconds and follows a uniform distribution. So there's our frequency table. Possibility of 1, 2, 3, 4, 5 seconds, equal probability of each of those occurring. That's why it's a uniform distribution. And there's a graphical representation of that. So we have formulas for calculating averages and variances for uniform distribution. So you can see the mean is going to be A plus B divided by 2, which is the lowest, plus the highest value divided by 2. That's what this formula is doing. So B10 plus B6 in parentheses divided by 2. So the average is 3 seconds. That's the average amount of time, which not surprisingly falls right in the middle. And the variance is going to be the square root of b minus a squared over 12. Okay, so for that one, there we go, square root. We need to have parentheses, whoops, just to protect the order of operations to make sure that is being calculated correctly. Okay, so the variance is 0.57. And we know the square root of the variance is the standard deviation, so if you wanted to, you could find that. Function of x is 1 over b minus a. So again, here we're looking at 1 over b10 minus 6. Let's use parentheses to protect order of operations. That does change the value there, so 0.25. And then the probability x is greater than 4 is another thing we're looking for here. So here we're going to do x minus a over b minus a. So here it's b10 minus b9 over b10 minus b6. All right, so that's one example. This is an exponential example. So it says let x equal the amount of time in minutes a postal clerk spends with their customer. Time is known to have an exponential distribution with the average amount of time equal to 4 minutes. And x is a continuous random variable. It's given with mean equals 4 minutes. So we need to know the decay parameter, which is m. So m is 1 over the mean. We know the mean is 4, so it's 1 over 4, which is 1/4 or 0.25, which is what we are calculating there. And then to complete the exponential distribution, we need to use this value of e, which is the natural log base. And we just bring it out to a few decimal places. This actually keeps going, but we're going to use it just out to the 5th decimal place, which is going to be pretty accurate. And then we'll use this equation. So the function of x equals m times e, so 0.25 times 2.718 raised to the minus mx value. So m again, 0.25, x is the number of seconds, so 0 down through 10. And so we have that formula going in the fx column here. And it just changes by altering what x is as it goes down the rows. And if we plot this, we just highlight the probabilities, and then we're going to insert a line graph. Okay. And that's how we got the exponential distribution showing. And finally, we come to the normal probability. And this will be useful for a lot of purposes throughout the semester. And so, very important topic. So this problem says, for the SAT, determine the z-score, that is the number of standard deviations and the direction that each of the following scores fall from the mean. The mean is 500 for the population of people taking the SAT with a standard deviation of 100. So determine the probability of exceeding that score, which is the area to the right. So 500 is the mean, right? So what we do is we make a table here. There's our formula for calculating the z-score, and that is going to be z equals x, which is the SATs that are scored for individual students, minus the population mean, which we got from the problem, divided by population standard deviation. And that is what it looks like when we translate that formula into an Excel equation. So B6 minus 500 over 100. The numerators in parentheses for the order of operations. Okay, so that's a 0, right? And B4 is a 1. So where do these probability values come from? That's the next question. So we need to use our z distribution, right? So we can see that a 0 value, which is going to be all the way down at the end, it's going to be 0.5, right? So we're looking above, which is going to the complete opposite end of the curve, right? So we're looking at 1/2 of this distribution. So probability of being above the mean of 500 is going to be 50%, or half the distribution. The probability of the entire curve, of the normal curve, is 100%, or 1.0 proportionally. But about a 400, so that's a z of minus 1. All right, so minus 1 is going to be over to this side. You can see 75% of the distribution is over a minus 0.68, so minus 1 is even further to the left. So it's going to be more than 75%, or 0.75. Okay, so let's see, we've got z of minus 1 we're looking at. So this is symmetrical, so even though it's positive, you can look at it both ways. So on the positive side, at 1, we're looking at 0.34. So we're looking at the area to the right of that. So we're looking at the value beyond that. So we're looking at 0.84 for the z distribution. So it's going to be 0.5, which is half of the distribution, plus the value we see here is 0.34. So 0.5 plus 0.34 is 0.84. That's how we got to that value. And for 1.5, which is going to be way over here, it's almost nobody scores above that, so it's going to be a very small proportion. So it's going to be 0.5 plus the value associated with 1.5 here. So 1.5 is 0.43. So 0.5 plus 0.43 is going to be 0.93. Right? To the left, since it's positive. So only 7% are going to score better than a 650. So I don't know if you saw how I did that. So I took the 0.93 and I subtracted it from 1, which is the total probability under the curve. So 1.5, if you imagine it's going to be somewhere about right there. And we're looking for the probability to the right. And what we're getting from the table is what's on the left. Okay, so we got 570 here. So that's a 0.7. That's going to be pretty close to this 75% level, so that would mean 25% over to the right, or 0.25. You can see it's 0.24, right? So again, now we're looking at 0.7, so 0.258 plus 0.5 is 0.758. Subtract that from 1, and you get 0.24. So this is just rounded up to 0.26. 0.5 plus 0.26 is 0.76. 1 minus 0.76 is 0.24, so the area to the right. What about a 750? That's a very difficult score to achieve, so I go to 2.5, and you get 0.49 plus 0.5, so only 1% remaining to the right of that. 0.01 as a proportion. Probabilities are usually shown as proportions instead of percentages. 380 is really a low score, so that's a minus 1.2. It's going to be way over here, so most of it's going to be a high proportion who are to the right. Right? So now let's go to 1.2 on the table, and that's 0.38 plus 5, or subtracted from 5. Right? Will give you the area to the left, which is going to be 0.22. So subtract 0.22 from 1 to get the area to the right, and you get 0.62, right? So yeah, I probably said that wrong, but yeah, you got the point. 0.38 to the left. No, I didn't need to add the 0.5. That's what the problem was there. Okay, so we're just looking there for this one, minus 1.2. So 0.38 gets us the left side of the equation. And then so what's left, 0.32, or 0.38 rather, is 0.62. Okay, so that's how we calculate the probability to the right of that value. All right, so that's how we use the normal distribution. It takes a little bit of practice and getting used to. It's very useful for confidence intervals and hypothesis testing, as we'll see later on. Thank you.